speaker is Joseph Lukens from Oak Ridge, talking about photonic quantum information processing with spectral qudits.
Well, all right. Thank you for that introduction. It's an honor to be here, and thank you all for staying out through the last day. I hope it's worth your time. So here is my topic today is going to be photonic quantum information processing with spectral qudits, a thing that we've been very interested in at Oak Ridge National Laboratory in collaboration with researchers at Purdue University as well. So first, an overall outline of what I'm going to call frequency bin quantum information processing, or QIP. What are the components that we need and the things that I'll talk about today in realizing each one of these steps? Well, of course, the first step is that we need protocols to use this particular degree of freedom, and I'll discuss that in more detail. And then I'll move on to actually implementing some of these gates experimentally, and finally realizing true verifiable quantum interference in this paradigm as well. So first, moving on to protocols. So why would we be interested in the first place in this time-frequency space of quantum information, and in particular of photons? And really, time frequency is kind of new on the scene, so to speak, in that, especially if you're considering photons, things like polarization or spatial mode have a longer history in quantum information. But I think time and frequency has a lot of fascinating advantages. In particular, it's compatible with single-mode optical fiber. It's how we communicate classically. And it can allow you to do very sophisticated encoding schemes that are stable over long distances. And there have been a few very interesting protocols proposed that differ depending on, are they discrete or continuous encoding, what are the particular photonic modes in which information is encoded, and what type of processing is realized. Most of the time, these gates are implemented using some type of optical nonlinearity. So you have a strong optical pump field that mediates a particular interaction. But there has been at least one example of a truly linear approach in this time bin space. And you can see in the lower right-hand corner an example from Oxford a few years ago showing linear optical quantum computation, LOQC for short, in time bins and using polarization rotation and probabilistic gates. And this idea of LOQC has been around for a while. It was originally proposed by Natl, and Milburn in 2001. And it's interesting in that it only requires linear optical components like beam splitters and phase shifters. And its multi-qubit gates are realized probabilistically by getting particular photo detection combinations. And even though this can be a challenge to build up, it is in principle scalable. And one thing that we like about linear optics is the fact that the noise is extremely low compared to nonlinear optical approaches. So we seek, and what I'll talk about today, is developing the first discrete linear optical QIP protocol using frequency modes. And frequency bins in particular, I think, are very attractive for some of the features I mentioned before with compatibility with optical fiber. And of course, the frequency combs make a lot of sense with wavelength division multiplexing as well. So we already have the classical toolkit, so to speak, to work with these modes. And what I also think is quite interesting is that in the last couple years or so, there's been some fascinating work in integrated quantum frequency combs, so generating entangled states over many different frequency bins on chip. And so that's, I would say, a main motivator for our work as well. We want to be able to have a paradigm that really matches with these types of entangled states, and that allows us to do universal and scalable quantum information processing. So that's somewhat of the motivation for looking into and trying to develop what we call spectral LOQC. So to do that, we have to figure out what do we have at our disposal in order to really control and manipulate these states. And I'm going to focus on two major technologies. The first one is Fourier transform pulse shaping. So you can see an example, a schematic of a pulse shaper in the center of this slide, where you take a broadband optical frequency field, use a diffraction grating to spatially separate the wavelengths so that you can independently control the amplitude and phase of each one of these different frequency elements. And this actually allows you to synthesize an arbitrary frequency spectrum. And when you put the frequencies back together, you can get a very complex waveform with femtosecond scale features, even though you have a temporally fixed physical arrangement. And so this technique has been around for really decades now, and it's ubiquitous in ultrafast optics and even in optical communications. And I just show some classic experiments in classical optical pulse shaping. I picked these in particular because over the last 10 years, there have been several interesting experiments that actually implement these same ideas using single photons or two photon light as well. So these experiments are actually physically quite different than their classical counterparts. Here we're showing temporal correlations between two photons. So it's not a single photon experiment or an intensity pulse shaping, so to speak, as it would be in the classical case, but really shaping of correlations. But nonetheless, the actual shapes that are realized can be very similar. And so what I think is fascinating about this is that it demonstrates that this technology that we take for granted in classical optics works just as well at the single photon level. So this is a very useful tool that we think has been really underutilized in quantum optics to this point. And the second technology that I like to highlight is also very standard in optical communications, known as electro-optic modulation, phase modulation in particular. So in this case, you can have a crystal that has that has the electro-optic effect, where if you apply a voltage across it, you can change the refractive index. And if you apply a very rapid voltage, you can modulate the phase of an optical field at gigahertz rates or faster. And so these modulators, of course, have been used in generating things like optical frequency combs, delay lines, spread spectrum communications. So these are all, again, classical examples. And perhaps unsurprisingly, over the last decade or so, these have all been applied at the single photon level as well, and shown very, very interesting experiments manipulating single light quanta. So I think this is quite encouraging if we're trying to build up a paradigm for really manipulating frequency bins in the quantum space. We can take full advantage of what has been developed in classical optics. So with that, I'd like to actually propose our protocol, spectral LOQC. So we have all the tools at our disposal now to try to build this up. So I first assume that we have some frequency comb, so equispaced modes, and these are going to be the Hilbert space in which we work, and we populate these modes with photons. And so a single qubit will be a photon that can exist in a superposition of two of these frequency modes. And to change the phase of each one of these modes, we will use a Fourier transform pulse shaper. And we'll assume that we can do line-by-line shaping, so we can resolve each one of these spectral components independently. And this actually makes a lot of sense at kind of the spacings realized in, say, dense wavelength division multiplexing. And finally, we also need to be able to mix these modes coherently. And to do that, we can use the electro-optic phase modulator, or EOM. And we assume here that it is driven by some waveform that is periodic at the mode spacing. So this means that a single mode will have side bands at this particular spacing that will allow it to interfere and overlap with other frequency modes. And this operation is actually fairly complex. It will, in general, spread the photon over many different modes, both higher and lower frequencies. And so this can be an advantage, but also a challenge. So for example, if you come in with two frequency modes, I use rails here to define different frequency modes. Just for pictorial purposes, this is actually all in a single spatial mode. But if you come in and say two modes A0 and A1 through a single EOM, you will actually create sidebands that will make you leave this Hilbert space. And that actually means that your operation will, in general, suffer from scatter problems, and you might have a low success probability because you'll actually exit the computational space that you're working in. And so this is actually, I would say, from a technical side, the fundamental challenge that we need to address as we try to build up this protocol. So the main questions then are these elements sufficient for universal QIP? So I've just proposed them. Can we actually do a full universal gate set? And are they scalable? And thankfully, the answer is the affirmative, and I'll explain why now. So to do that, we explicitly set out to derive a universal gate set, and we do that numerically. So we need to get a universal set that includes single qubit gates and then also a 2-qubit gate. And we do that by proposing a particular configuration of pulse shapers and EOMs and searching for the phase values that allow us to maximize the fidelity and success probability, so F and P, to realize a given gate. And in the single qubit case, the phase gate, and I use phase for all sorts of different gates because it's very easy in our paradigm to apply an arbitrary phase to each one of these frequency modes. So this could be a T gate or any other combination of phases you would like. And this actually kind of comes along for free with our paradigm. That's good. The Hadamard gate, on the other hand, is a big challenge, and that's because even though you can get two frequencies to mix with an EOM, you'll create these extra sidebands, and that actually reduces your success probability. You get effectively scattering loss. And what we discovered is that if you do a series of not a single EOM, but an EOM and then a pulse shaper in between that changes the phases of these modes, and then another EOM, you can actually, even though you spread out your frequencies, you can bring them back together into the original two-mode subspace, and you can get a Hadamard gate with 100% fidelity and success probability. And these are the actual numerical solutions, the temporal phases and the spectral phase shifts applied. Again, not horribly illuminating, and these are not unique solutions by any means, but they do indeed work, which is what we're trying to show. And of course, the big challenge in optics is doing the 2-qubit gate, and in our linear optics paradigm, we can only do this probabilistically, and in fact, the best known controlled Z gate, which is what we're showing here, in linear optics succeeds with probability 2/27. This would be using non-entangled ancilla photons. And we actually were able to find a solution with very similar performance to the best known case in general linear optics. So we have these triangles are two ancilla photons that we send into these particular frequency modes, and then the A's and B's are the modes of the two interacting photons that we're doing a CZ gate. And we have detectors. When we get this particular click pattern at the output, then we know our gate succeeded. And we find that we can get 100% fidelity, or very, very close to that, and a success probability right at 2/27 as well. And this is important for us in that it shows that the devices that we have proposed really can do the best, or can succeed with the best possible known 2-qubit gate in linear optics. So we have a universal gate set, and further simulations showed that even though we do have this somewhat unwanted scattering into adjacent modes, with, like I said, this is a consequence of using an electro-optic modulator, which means that we might need to have some kind of guard bands beside our gates so that we don't have crosstalk between, say, gates performing in one frequency band with those performing in another frequency band. But we found that even though we do need some of these extra modes, it's fairly reasonable compared to our computational space. And we also note that the number of components needed scales linearly with the number of modes. And again, this is important to show that our paradigm really is, at least in principle, scalable. So that's a very important finding, and it's based on decomposing matrices into products of circulant matrices, which are like what the EOMs do, and then also diagonal matrices, which is what the pulse shapers do. So this is the complete theory for our protocol, and I invite you to look at this reference if you're interested in finding out more information. But I'm an experimentalist, and I really want to actually start implementing these things in the lab, and we have been able to begin making strides in that direction. So I'll first focus on the single qubit gate, and I'll actually generalize a little bit to qudits, so perhaps higher dimensions as well. And the big challenge when we're talking about frequency is getting multiple frequency modes to mix and with high success, so we don't lose a lot of our photons into scattering into unwanted modes. And so we focus on the discrete Fourier transform, or DFT. And of course, the D equals 2 case is the Hadamard gate that we're all familiar with. The D equals 3 case is actually a balanced frequency tritter. And so in optics language, a lot of times we would say beam splitter and tritter. And this trigger actually has not been explored at all in the context of frequency bin quantum information. Beam splitters, on the other hand, have been explored just very recently using nonlinear optics, as I said, kind of the alternative to our linear approach, where they actually have powerful optical pump fields to mediate the interaction between two different frequency bins. So you can see some of those examples here. And they're exceptional experiments, but they suffer from a lot of noise from this strong pump fields, particularly things like Raman scattering or imperfect isolation of the pump from your photonic or single photon frequencies. So in our experiments, we're looking to do the first electro-optic frequency beam splitter and the first ever frequency trigger. So I just want to highlight the differences here. So this is our experimental setup. Our frequency beam splitter, the core, is in the center here, and we have an EOM and then a pulse shaper and another EOM. We found that we don't need the initial pulse shaper to do a frequency beam splitter that we had in our original solution, so we could simplify a little bit. And from a technical side, we also found that even if we drive our EOMs with a single frequency sine wave, which is a huge simplification experimentally, so we don't need an arbitrary waveform generator at, say, 25 gigahertz type repetition rates, we found that even though we still have some scattering into adjacent modes, so it no longer has 100% success, it actually is very high. So these are numerical results that indicate we have about 97.6% success. So we have only about 2% scattering into adjacent modes with this huge simplification. So that was very important for us in taking our theoretical ideas and applying them in the laboratory. And for these experiments, we use a classical frequency comb to do the probing, and we can attenuate it to the single photon level as well. So that allows us to create superpositions of these different frequency bins. And to go to the trigger, we found that we do need slightly more complex RF components. So a single frequency was not enough to do a high fidelity, high success trigger. But if we add the second harmonic RF component, we can actually perform very well. So here you can see we have a frequency doubler, and in the trigger case we work at an 18 gigahertz mode spacing so that we have a 36 gigahertz tone that we add in phase, or add with a particular phase with our 18 gigahertz signal as well to get the specific waveform we need for the trigger. Oh, and I will point out the main disadvantage of our approach currently is that we have high loss. So the gate loss right now is about 12 dB, and this is we're buying off-the-shelf telecom components. So they each have a few dB loss per component, but we think this can be significantly reduced, although it will take some important engineering. I will emphasize that the loss is not intrinsic to our method, so the operations that we're implementing are phase only, they're unitary. So this is just an insertion loss, a technical issue, not fundamental to the method. So here are our results for demonstrating a frequency beam splitter. We use our classical frequency comb to characterize the fold transformation matrix. So we have very high fidelity and high success probability as expected. And just so you can visualize that really this is performing like a beam splitter but in frequency space, we show a few examples here. You see that if we send in a single line in either mode 0 or mode 1, and these modes are spaced by 25 gigahertz, we get a superposition at the output. Likewise, if we send in a superposition at the input with the right phases, we can send all the energy either into mode 0 or mode 1 at the output as well. And what's especially interesting, I think, about our operation is that it's readily parallelizable in that we can perform many of these gates in parallel in frequency space just by scanning the center frequency of the interacting of the two modes that we're interested in. So you can see doing that actually explicitly, we find that we can maintain above 3 nines in fidelity and above 96% success probability over the entire communications band, 40 nanometers, around 50 center wavelength. And we can also pack these very tightly and still have high performance. So if we put two beam splitters too close in frequency space, there'll be some crosstalk. But we found that if we put roughly 4 empty modes in between, that we see essentially no degradation in performance. We can treat them as effectively isolated, and that's what the second plot shows. And so combining all these results, if we have 25 gigahertz mode spacing, we actually find that this implies we can do 33 of these beam splitters in parallel. And so this is, one reason we started looking into this was we were interested in all the advantages of classical wavelength division multiplexing. And here's a direct example of doing our frequency beam splitter in a WDM compatible approach. And here are the results for the frequency tritter. We also see high fidelity, high success probability, and you can see our examples. If we now put in our input in mode 0, 1, or 2, we get a 3-mode superposition at the output. And if we send in superpositions at the input with the right phase, we can localize all the photonic energy in one of the 3 possible output modes. And of course, because our device is linear, so what we do at the coherent state level also works at single photon level. So when we attenuate our input state to roughly 0.1 photons per detection window, we send in a superposition in this case and scan the phase, we see the expected interference fringes when we count photons in each of the output frequency modes. So for the beam splitter, you can see as we scan the phase, we initially send all our energy out in mode 0, then it changes to mode 1, and then back to mode 0. And likewise for the tritter, when we send in a 3-mode superposition and scan the phase, we can again see interference fringes in the photon probability in exiting in each one of these output modes. And mode 1 has a lower count rate than the others, not because of the gate, actually it's because of the filters we use to separate the frequencies at the output. Mode 1 happens to be closer to an edge and have higher loss, but our gate itself performs the same for each one of these modes. And these results recently just published in PRL. You can find the reference here. And for the last part of my talk, I'd really like to emphasize or take this a step further and show really true quantum interference. So the last things that I showed, even though when we went to the single photon level, they really can be understood classically as essentially the performance that we have for high power coherent states is really the same for single photons. We didn't really explore something that looked at uniquely quantum effects. But of course, if we want to build this thing up, we'll need to be using quantum effects. That's the whole point in looking in quantum information processing. So in our full vision, we really like to imagine what we would call a quantum frequency processor, where we could be doing many of these operations in parallel in a single spatial mode, and perhaps different operations as well in parallel. And to begin looking at this, we focus on 2 fundamental effects in quantum optics. We focus on Hongel-Mandel interference, HOM for short, and Einstein-Podolsky-Rosen, or EPR, correlations. So effectively, correlations in complementary bases that we'll see with particular types of entangled states. So when we want to look at the non-classical interference phenomena, our experimental setup is actually very similar, except on the generation side. So now we're not looking at a classical frequency comb, but rather a 2-photon source. So we have a Ti-sapphire laser and a periodically pulled lithium niobate waveguide to generate entangled photons at 1550 nanometers, which we then filter with an etalon with a 25 gigahertz spacing. So this is how we get our biphoton frequency comb, and our quantum state really can be approximated as a superposition of these different frequency pairs, as shown here. And then we go through our quantum frequency processor. I'm using a more general term because we're going to apply more generic combinations of gates. And just to show what our source looks like, you can see this is the coincidences between different output mode combinations. And you find that as you scan the mode, the filter for detector B or for detector A, we see a high coincidence peak when you have energy matching, and then we see effectively no coincidences on the off-diagonal portion. So this just shows that we really are generating a near ideal state for probing our system. And of course, the way we generate this is not particularly interesting. We could use much more exotic sources such as microwings to do this, but we just really want a test quantum source to characterize our system. So the first thing I said I want to show is frequency domain Hongel-Mandel interference. And so what this entails is we have two photons in two different frequency bins, or one photon in one bin, one photon in the other. And if we go through a frequency beam splitter, we should see bunching at the output. So we should either see both photons exiting in the same frequency mode or in the other frequency mode. We shouldn't see coincidences between the two. And then we need some way to tune the distinguishability of these interfering paths to get kind of a dip, as you would expect in the traditional HOM experiment. And with the previous beam splitters shown with nonlinear optics, they have actually explored Hong-Mandel interference. Here are a couple examples, and you see the visibilities are around 70%. Now, the classical limit is 50%, so this is verifiably quantum, but the visibilities aren't that great either. We'd like to get a much higher quality interference, and that was one of our goals as well in entering this space. And to do that, in our case, we actually noted another advantage of our approach is that we can actually tune the reflectivity of our frequency beam splitter by changing the spectral phase applied by our pulse shaper. And so this is actually the parameter that we use to map out Hong-Mandel interference. And I think this will make more sense when I show the experimental results. So first thing, this tunability on this left plot, this shows the transmission and the reflectivity of our beam splitter as we scan this phase. And again, this is using coherent states to characterize. And you see that our reflectivity starts off at 0. So I'm saying reflectivity is essentially the hopping probability to jump from mode 0 to mode 1 or vice versa. And as we scan this phase, the reflectivity goes up to 50% and then goes back to 0. So you would expect really right at a phase of pi radians that we should see maximum interference and then no coincidences in the Hong-Mandel case, which is indeed what we find. So when we send in one photon at frequency omega 0, another photon at frequency omega 1, and then we scan this phase, we see a large number of coincidences until we get to pi, and then it drops to very close to 0, and then it comes back up. And if we map out this visibility, a fit function shows a visibility of 94% without any type of accidental subtraction, which is by far the best shown in frequency domain HOM interference. And again, this is a key consequence of the low noise in our system compared to nonlinear approaches. And we like to go even further. The HOM experiment showed that not only do we have an operation that can be done in parallel in the frequency bands, but we can also tune this operation changing the spectral phase, which means that we could not only do operations in parallel, do the same operation in parallel, we could actually do different operations in parallel in the same device by changing the spectral phase in different bands. And we actually exploit that directly for manipulating now a 2-qubit frequency entangled state, where we apply either the identity or the Hadamard operation to different parts of our, or different qubits. And so if we start off with a frequency entangled state that has negative frequency correlation, so the frequency you measure of one, if it goes up, the measurement on the other one goes down by energy conservation. We have different possibilities. If we then apply the Hadamard to one of these two photons, we essentially erase these correlations, so we see a uniform population in our 2x2 space. But if we apply the Hadamard to both, we retrieve correlations again that are now flipped, so they're now positive correlations. And so this is a way to show that we can do coherent control of our quantum state in this setup. And these are the results showing that for all different combinations of the Hadamard and the identity operation. And you can see when we just look at the identity and we look at correlations between the frequency bins, we see exactly what we expect for energy conservation. And if we apply a Hadamard, then this gets spread out over the 2x2 2-qubit subspace. And then if we apply the Hadamard to both, we again retrieve correlations, but now in a different sense. And we show actually coincidences in the neighboring modes as well, just to show that we don't have significant scattering as well in our system. So we really have a closed quantum operation. We start with 2 qubits and we end with 2 qubits, which again is an important part when you're talking about optical manipulation. And we can quantify this with the conditional entropies for each of these cases. the conditional entropy for measuring a particular frequency on A, given knowledge of the measurement result on B. And if we use the match cases and sum them up, we actually have a form of an entanglement witness. And we find that we violate the condition of separability by about 10 standard deviations. So this, again, shows that we're able to control and measure these entangled states. So as we think about applications, of course, photonic quantum computing would be fascinating, but we realize that we don't want to put all our eggs in one basket. We think that this is a useful approach for general quantum information processing in many platforms, particularly for potentially interconnecting matter qubits of different frequencies. We think by doing these frequency operations that is a good possibility. And actually, our hosts here in Bilbao have recently proposed an interesting idea of photonic quantum memristor using tunable beam splitters, and we think that perhaps a tunable frequency beam splitter could be applied in this context as well. So with that, I'd like to acknowledge the other authors on this work, our team at Oak Ridge National Lab. Pavel Lugovsky is the PI there. And then also our team at Purdue University. Peach Liu, the student, did much of the experimental work, and Andy Weiner, his advisor. It's actually my former advisor as well. I graduated from Purdue a few years ago. And again, here are references and also archive citations as well if you'd like to learn more. And thank you so much for listening.
Thank you for staying in time. So, questions?
I could not reconcile in the middle of your talk. You were announcing a gate loss of 12 dB, and yet you had a success probability close to 1.
Yes, so we do make a distinction between the intrinsic success probability, which is effectively the chance that our photon gets scattered into different frequency modes, and the insertion loss. And the reason we make a difference of that is because the insertion loss is a technical feature of, we have between, for example, our fiber waveguide interfaces, we have lots of loss, whereas the success probability is actually a function of the types of waveforms that you modulate. And so the success probability is really kind of, if we had no loss in our system, this would be how well the gate would perform just in unitary evolution. But we also have this huge technical problem of loss. But we want to make sure that we can characterize both so you understand the contributions to both. So the success probability is just kind of the unitary scattering. And that's how we make the distinction there. Oh, absolutely. Absolutely. So I don't want to downplay that at all. So we're very clear that what is being, in that number success probability, that's what it's specifying is very specific. And so moving forward, we really need to work on that loss. I mean, there's no question about that. So.
One last question over here, back.
I have actually two probably brief questions. The first one is, so you said that you were going to aim for a scalable system, but the probability of success of this control set is very low. So how are you going to address that, or is there any way of addressing that?
Sure. So if you're particularly talking about the 2-qubit gate, I mean, this is a known problem with linear optics. So a lot of times you need to use ancilla systems and things like this. So it is, in theory, scalable. But you're right, it's a big challenge, and that's why a lot of people have been moving away from linear optics. But there are, I would say, not just using, in the basic circuit paradigm, for example, using cluster state quantum computing in linear optics, where you build on some of these things, but you can scale a little more efficiently. So I guess I'll make a distinction between practical scaling and theoretical scaling. So even with low success probability, you can have theoretically decent scaling. But again, practically speaking, optics is still at a level that's going to be very hard to compete with systems that can do deterministic 2-qubit gates. So I'll be completely upfront about that.
So I think the second one is shorter. So your encoding is kind of a frequency modulation encoding, no? Would you think that CDMA encoding would be better in these kind of situations? Code division multiplexing?
I'm sorry, did you say CDMA?
Yeah, code division multiplexing instead of
That's right. I actually have been thought about actually CDMA and quantum information for a while. There was an experiment that I showed kind of quickly back there where we actually did some CDMA encoding on entangled photons. And I think there would be a lot of interesting possibilities. When I was working in that area, the orthogonality of the CDMA codes in classical communications didn't seem to line up to the type of orthogonality I needed in quantum systems. So that was at least some of the challenges that I was having when doing it. So I think CDMA could be useful, but I, at least at this point, don't have a good paradigm to really map directly to things in quantum information. I think building that gap would be phenomenal, and I think it could lead to some resource improvements as well. So I think you bring up a good point.
Thank you for your questions. So we can move now to the next speaker.